Hey, welcome back everybody. My name is David Rodriguez and we're ready to get started here. So today we're going to be covering fire behavior and how that relates to us in the fire service. It's going to be pretty important that we understand how that fire behaves and how it reacts. Overall, fire is pretty predictable. Even though it reacts differently in different situations. So if you can understand the different situations and environments, you'll have an understanding of how that fire is going to react. And if you know how it's going to react, you know how to fight it. So let's get started. Alright, so we need to understand a few things about fire and the processes of it. The reason why is if we know what's going on with that fire, we know how to react to it and how to get ahead of the fire, how to keep it from getting ahead of us. Everything's going to burn and react differently. We know that sometimes different fires are hotter than others. Plastics are going to burn hotter than most of our natural fibers. So those are some things that we know already, and we're going to talk maybe a little bit about why some of those things happen. We're going to talk about how fires are classified and why that's important. Because if we can recognize how fires are classified and what it is that's burning, we know what it is that we need to use to extinguish that fire. We don't want to put water on an electrical fire. Then we need to learn the different conditions that exist that lead to super extreme conditions that trap and kill firefighters. We need to learn to be able to read and recognize those conditions so that we can predict what's going to happen and make an escape or make some type of intervention on a fire ground to prevent those things from happening. So fire it's a science. We're going to go over the whole science of fire behavior. But all fires, no matter what it is that's burning or the different classes of it, all fires are a heat-producing chemical reaction between some type of fuel and oxygen or similar substance. You'll see some kind of different definitions of fire, but this is pretty much the one that you need to know. I was always taught in the Fire 1 and 2 class that I should be able to memorize this and recite it. If I'm ever put on a stand or in court, if I can't give you the definition of fire or tell you what fire is, then I'm probably not a very good credible witness for fire, what a fire is. So we talked about the fact that there's a chemical reaction between a fuel and oxygen. That chemical reaction between that fuel and that oxygen is called oxidation. Oxidation can either happen super slow, like something rusting, or it can happen really, really fast, like an explosion. Fire sits somewhere kind of in the middle. Fire is a rapid oxidation process that results in the production of heat and light. So it's not quite an explosion, but it's a little bit faster than something rusting. So combustion is a chemical process of oxidation fast enough to produce heat and light, or like a flame. So we're going to learn that there's different types of fire, or there's flaming combustion, smoldering combustion. So we're going to see what those are as we go along in the chapter. Energy. So if we've ever taken a basic physics class or just high school science classes, we've learned that there's kinetic energy and there's potential energy. In this class, the most important thing for us is going to be the kinetic energy. That's what's going on. Potential energy is just energy that's stored and is ready to be used and released. Kinetic energy is energy that's being released, and that's what matters to us during a fire, because that energy is heat. So that energy that we were just talking about is measured in joules. A joule is the amount of heat required, 4.2 joules is the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. This is a lot of physical science stuff, probably taking you all the way back to 7th and 8th grade, but it is some important things that you'll definitely want to remember for the test. Bridge thermal units, or BTUs, I'm sure we've all heard of it. Most of the time we're referring to our heating units for the house. BTU is the amount of heat that we need to raise the temperature of 1 pound of water 1 degree Fahrenheit. 1 BTU is the same as 1,055 joules. So they're kind of different. You see that the joules is metric, the BTUs is your standard. So when a reaction produces energy, it's called exothermic. Fire is an exothermic reaction that releases the energy as heat and light. And then there's some reactions that are the opposite. They're endothermic. They absorb energy. An example of that would be converting water to steam. So when we start transferring all that heat from one thing to another, we start to cause something called pyrolysis, which is the chemical decomposition in solid fuels. So if you've ever looked at a match, you'll notice that when the match is lit, there's a small gap between the fire and the matchstick. What that gap is, that's all the decomposing matter, the decomposing matchstick pyrolyzing. It's like off-gassing basically. And that happens once it gets to a certain temperature. What often comes next is combustion. So much the same as pyrolysis occurs in a solid, vaporization occurs in a liquid. So vaporization is the same thing as pyrolysis, except it's in a liquid. Pyrolysis is the same as vaporization, except it's in a solid. If that makes any sense or makes it easier to picture. So vaporization is a process that changes the liquid into a gas. We've all seen things heat up, even if you've seen, it's basically evaporation. And then the rate of that vaporization depends on the fuel, heat, pressure, and surface area. For instance, if you've ever spilled any gasoline, you notice that it vaporizes really quickly. You see the little vapors coming off, versus some other heavier liquids, they don't do that the same way. Gasoline off-gasses pretty quick, vaporizes, doesn't need to be nearly as hot. And that's what you get there. And once you have that off-gassing starting to occur, that vaporization, when you introduce an external source such as a spark, that can provide enough energy for ignition. And ignition is the process of the self-sustaining combustion. So not just getting it to flash, but to self-sustain and keep burning. Fuel can also be heated until it ignites without a spark, but that's called auto-ignition, and we'll talk about that here in a few slides. Once something's ignited, the ignition process continues, and production and ignition of fuel vapors continues. So it's just like a constant chain. It's just a constant wheel that's going through the. You get it lit once, and it just continually keeps relighting itself so rapidly that it's just one continuous fire. So pilot ignition is probably the most common and what you would think of anytime you think about starting a fire. That just occurs when an outside heat source starts the combustion process. So when you go to light your pilot light and you stick a lit match in there and you put that on, that's piloted ignition. Same as if you light a campfire or a candle, those are piloted ignition. You're taking something, an outside heat source, and introducing it to it so that to raise that product to its ignition temperature so that combustion can occur. Now, auto ignition occurs without an external flame or spark. So that would be if a product is sitting somewhere where it's able to get hot enough that it lights on its own. So the actual definition is a temperature to which a substance must be heated for ignition and self-sustaining combustion to occur. In those instances, the fuel is chemically heated to where combustion starts. And the fuel's auto ignition temperature is always higher than its piloted ignition temperature. So, just going to use some magic numbers that don't really mean anything, but let's say that you have a substance and its piloted ignition temperature is 500 degrees. So you have to have a match lit that's burning at 500 degrees or greater to get whatever that substance is to ignite. Now, its auto ignition temperature might mean that it's just sitting there in the street or wherever, and it's got to reach 700 degrees before it will just catch on fire. That's kind of the difference between the two, if that helps at all. And then, of course, we have combustion, which is just a rapid and self-sustaining chemical process that yields heat and light. So to help us understand the process of combustion and what all it entails, we've developed the fire triangle. Well, the fire triangle is a simple model that shows what's required for fire. However, as time progressed and as our understanding of fire progressed, we realized that the fire triangle doesn't necessarily show us what we need for fire as we think of it with flaming combustion, but it really shows us more what we need for a non-flaming or a smoldering combustion. The three legs of the fire triangle are heat, which is characterized by the molecules moving around and vibrating to a point that it's capable of supporting a chemical reaction. The fuel is the material that contains combustion under that maintains combustion under certain conditions. And then oxygen, of course, is what is the oxidizing agent. Remember, the oxidizing agent we talked about earlier. So this is, like I said before, it provides the explanation of a non-flaming or smoldering combustion. To have a flaming combustion, what we're used to when we think of fire, we have to add the fourth leg, which is a chain reaction. It's a self-sustaining chemical chain reaction. Flaming combustion involves fuel being oxidized in the gas phase. So that's where, like I said, if you were to light a match and you see that small gap between where the match head is and the top and the bottom of the flame, that area is where the gases are being oxidized. And in order for those gases to occur, either it has to vaporize if it's a liquid, or it has to pyrolyze if it's a solid, and that happens once it's heated to its temperature. In order for the flaming fire to be there, all four legs of the tetrahedron need to be present. So once we get combustion going, we got the fuels burning, And all these chemical chain reactions going for the fire tetrahedron, we're going to have some byproducts of the combustion going on. The two main ones are heat and flame. And heat's going to be the big contributing factor to fire spread. Flame, that's the part that we see, that's the visible light. Then the third product of combustion is probably the most common, the one that you see, and that's smoke. And smoke is nothing but a product of incomplete combustion. What's in that smoke is always going to vary depending on what's burning. You've seen some smoke that's a black smoke, just like what we're seeing here. You've seen other smoke that's a yellow, acrid smoke. And then sometimes you'll see a light gray, puffing smoke. It all depends on what it is that's burning. And in that smoke, there's a mixture of gases, vapors, carbon, particles, and that's the soot. Sometimes you'll actually see little particles. That's the ash and stuff that ends up on your helmet and all over everything. That's all generated by the burning materials. So those particulates that we just talked about, can be inhaled into the trachea and lungs. That's why we wear a mask and an SCBA, so it shouldn't matter to us.
The time is 2100 hours. Attention drivers of all fire department vehicles, exercise caution while responding to all alarms. All individuals riding on fire department apparatus should wear seatbelts at all times. All companies operate the confirming keys.
Carbon monoxide is the most common fire gas created, and that's nothing but a byproduct of incomplete combustion of carbon-based fuels. Big thing about carbon monoxide is that it's odorless, colorless, and tasteless. You don't know it's there, and it can be toxic even in small quantities. Exposure to CO decreases your ability to carry oxygen in the blood. CO binds to the hemoglobin 300 times more effectively than oxygen does. So you can see why it can be quite the hazard. A few little common sense things about CO. The more there is, the longer you're in it, the worse off you are. Another thing about CO is that it has a wide flammable range and a low ignition temperature, even lower than methane or propane. And then another big issue for firefighters is that it's going to remain for a long time after the fire is actually extinguished. A lot of guys like to take off their SCBA once the fire's out. Yeah, the heat's gone out of the building, but those toxic gases still remain. Carbon dioxide. A lot of times when we go on a CO run, people confuse carbon monoxide and carbon dioxide. Carbon dioxide is something that they hear more often, and it's used as propellant for soda machines and stuff like that. So it's something that they're familiar with. But carbon monoxide and carbon dioxide are two different things. Carbon monoxide is a chemical asphyxiant. Carbon dioxide is a simple asphyxiant. All it does is it displaces the oxygen in the air. Hydrogen cyanide. That's produced by the burning of wool, silk, nylon, polyurethane, and products containing nitrogen. So you can see that it comes from burning the old stuff that was in legacy buildings. Remember when couches were stuffed with hay and wool and plastics and the polyurethane. So hydrogen cyanide is going to be in almost every fire that we ever go to. That's a chemical asphyxiant that prevents the body from using oxygen at the cellular level. Oftentimes, some of the cardiac arrests that firefighters suffer post-fire are actually from hydrogen cyanide exposure. Hydrogen chloride, that's produced by the burning of polyvinyl chloride in building materials and furnishings. Anytime you see poly something, you can guarantee that it's some type of plastic and it's no good for us. Once that stuff burns, the smoke is usually thick, black smoke, and you can't tolerate it at all. It's not like the smoke from a brush fire or a bonfire, where you can take a little bit of the smoke. Yeah, it stings a little bit, but this stuff can kill you almost instantly sometimes. For instance, hydrogen chloride, when it mixes with water to form hydrochloric acid, it's corrosive to human tissue. Sulfur dioxide, toxic and corrosive. Hydrogen sulfide, produced by burning of rubber, wool, silk, and some synthetic materials. So pretty much everything that's in a building will produce that. Formaldehyde is a severe respiratory irritant. We all know formaldehyde is used in embalming. Heat, one of the other byproducts of combustion. I said earlier, the heat is the kinetic energy that comes from the fire. Heat's always transferred from a high temperature to a low temperature. So when you stick a bottle of water in a freezer, the refrigerator doesn't freeze the water, doesn't cool the water. The water tries to warm the atmosphere around it to a point that it gives off all of its heat. And we all know that when things get hot, the molecules all start to vibrate, and they're moving all around, and they get bouncing all over the place, and they start to break down. And that's when they start to break down, they release vapors, and those are the vapors that ignite, whether it be as a solid, which pyrolyzes, or as a liquid, which vaporizes. Temperature is simply the measurement of kinetic energy. Here in the U.S., we measure temperature in Fahrenheit. Everywhere else in the world, they use Celsius. Some numbers that you need to know as a firefighter: 32 degrees, that's when water freezes. Obviously important for our hose lines. 212 degrees Fahrenheit is when water boils. That's important so we know. I mean, that's when water vaporizes, turns to a steam, and that's where the cooling process begins. So we have a few different types of heat energy. First one we're going to talk about tonight is chemical heat energy. Chemical heat energy is the most common of the five. Chemical heat energy is a spontaneous heating. That occurs when the material's temperature increases without any external heat source. It's produced slowly through oxidation. Remember, we stated earlier tonight that oxidation produces heat. When you see iron rust, it actually produces heat. It just happens so slowly that heat is able to dissipate without you even noticing. Now, in a rapid oxidization process, such as an explosion or a fire, obviously there's heat produced. So if you're able to contain that oxidation process into an area where the air supply around a material will continue to heat and then be heated enough that it will support combustion, well, then you can have spontaneous ignition. Once you have spontaneous ignition, that's like spontaneous combustion. That's what we hear about, where the old lady's sitting in her rocking chair and then she just bursts in fire. Well, that's not going to happen. But what we will have happen are hay bales or oily rags or something like that actually catch on fire. Going back to our example earlier with a piece of iron rusting, if you have metal shavings and you put them in a trash can or something airtight, well, as those metal shavings start to rust and oxidize and produce heat, if that heat can't dissipate fast enough, then they will actually combust, catch on fire. Mention the hay bales. Heat of decomposition. Organic materials decompose, and when they decompose, they produce heat. That's why we sometimes have the hay bale fires days and weeks after the hay's been cut. When that hay's cut wet, it sits in there and it decomposes. Same thing with our mulch piles. We'll see mulch piles steaming. That's what's going on there. Heat of a solution is released when a substance is dissolved in a liquid. Electrical heat energy, it's resistance heating. You see the example of the stove. As the electrical current goes around those coils, there's resistance, and that's what produces heat. An overcurrent or an overload happens when the current exceeds the design limits of the conductor. You can see that's the example of all the electrical cords plugged into one outlet. And then dielectric heating is a result of a pulsating current on a non-conducting material, such as a microwave oven. Arcing. When electric arcs, it arcs at extremely high temperatures, between 2,000 and 7,000 degrees. An arc can happen from static electricity or lightning. And sparking occurs when arcing occurs and particles spatter away from the arcing, just as a picture. Mechanical heat energy. This is one of the things that makes your car engine hot. Not only because it's an internal combustion engine and you have little explosions going on in there, but it's from the friction. As those parts move back and forth, they produce heat. If you were to take your hands right now and rub them together, you'll feel the heat. That's from friction. Heat of compression. If any of you have filled your SCBA bottles, you'll know that your SCBA bottles get hot. Because when you compress those molecules, those air molecules, they start to bounce around and they collide and they start bouncing around, and when all that energy happens, we have heat. Nuclear heat energy is generated by atoms splitting apart or combining. Not something that we'll really run into. Solar energy is just energy generated by the sun. How fast that energy transfers from one fuel to another is going to determine how fast that fire is going to grow. As I stated earlier, heat moves from warmer objects to cooler objects. The greater the difference in the heat, the greater the transfer rate. Heat flux is the energy transfer over time per unit of surface area. Heat flux is measured in kilowatts per meter squared. So now that we have all that heat and energy, we need to transfer it somewhere. And as we stated before, that heat is going to transfer from a warmer body to a cooler body. Conduction is when we transfer the heat through direct contact. Conduction would probably be the most common source of an accidental fire. In this case, it's started by a flue that's probably not lined properly or insulated properly. That pipe gets hot, touches the adjoining rafters, and starts a fire. Another example would be setting a pot of water on a stove. This pot gets hot because it's touching a hot element. How fast that conduction occurs depends on how big the area is that's being heated, the difference in temperature, and the material's thermal conductibility. All that means is it insulated? For instance, if you have a pot holder and you grab a hot pot, your pot holder is acting like an insulator. That's why you don't conduct the heat through the pot and onto your hand. Commercial insulators are often made of things like fine particles or fibers with void spaces between. It's that little bit of air in between them that helps to slow the transfer of heat, and that happens and works because gases don't conduct heat very well. So with convection, we have the heat moving through a medium of gases or liquids. As those gases and liquids circulate, they heat up the surrounding solid areas, solid surfaces. We know that hot air and combustion byproducts become buoyant and rise. We've all heard that heat rises. Convection can occur in any direction. However, convection generally occurs upwards as gas and smoke are heated. Within a structure, convection can happen laterally due to differences in pressure. So if you have a room with higher pressure than another, it's going to move to the room with lower pressure. Now if you get in the path of this convection current, that hot air and smoke rising, you're going to feel the difference. You're going to feel the speed of the air and the turbulence of those gases as they pass by you. Think of a chimney, and when you see that smoke rolling and turning out of that chimney, you get into that chimney, whether it be a hole by an opening in the floor or a basement stairwell. If you're fighting a basement fire, you're really going to feel that heat because you're going in at the top hottest layer of those gases. Radiation. Don't think of radiation as like a nuclear physics thing. Radiation is just the transfer of heat as energy traveling through space or materials as heat waves. Radiation is responsible for most fire development and spread. You can see in this picture there the neighboring garage started to ignite. They had the siding melting. So we'll see that quite a bit when we have two structures close together. Or when you get to a fire and you start to park too close, you get too close, when it's really rocking and rolling, the heat you feel is the radiating heat coming off of there. So radiant heat can travel through air spaces in vacuums. It won't end up in a vacuum, so we don't need to worry about that. For test purposes, it's probably important. Dark materials absorb heat more than light colored materials. Think of in summertime, what color shirt do you wear? A white shirt or a black shirt? The greater the distance between the heat and the exposed surfaces, the less effective radiant heat. Simple time distance shielding. The farther away you stand from the fire, the less heat you're going to feel. Time, you just reach over and you throw a stick in the fire real quick. You don't notice the heat is bad and you won't get burned. And shielding would be when we wear our structural turnout gear. It's something that protects us, creates a buffer from the heat. One of the things about radiant heat is that it increases dramatically as the heat source increases. So even though the structure fire is only doubled in size, the radiant heat has actually quadrupled in size. So it grows exponentially. In a structure fire, firefighters are going to encounter all three of these types of heat transfer, whether it be crawling over a hot coal, conduction, or crawling through the basement, going down the basement stairwell, convection, or radiant heat when we're just walking up to the structure and we can feel the heat coming off of it. So fuel is just the material being oxidized or burned in the combustion process. Referred to as a reducing agent because that's what's being consumed or reduced. As firefighters, most common fuels that we're going to encounter are organic and contain carbon, whether it be a hydrocarbon-based fuel such as petroleum or plastics, or a cellulose-based fuel like wood or paper. However, we will occasionally encounter inorganic fuels such as hydrogen and magnesium. None of those contain carbon. A fuel's chemical content is going to dictate just how hot it burns. And the heat of combustion is the total amount of energy that's released when a fuel burns. The heat release rate is the amount of heat that's released per unit of time measured in kilowatts and megawatts. Flammable liquids, for instance, have a much higher potential for heat than heat or thermal energy than a natural product like wood or paper. And power is the rate in which energy is transferred. With fire, power is in the heat release rate during combustion. Heat release rate depends on the type, quantity, and orientation of fuel. Orientation is important because what that means is the fuel standing or laying down? Well, we know that a fire burns faster uphill than it does downhill or on flat ground because heat rises and it preheats the fuels above it. Fuel's combustion is influenced by the fuel's physical state and its distribution. Is it in a solid, liquid, or gas form? Fuels that are in a gas are the most dangerous because they're already in the form that's needed for a flaming combustion to occur. Okay, going back to a 7th grade physical science class, we're going to talk about the different states of matter and how they relate to the fuels that we're going to encounter. Any fuel that's already in a gaseous state, such as propane or natural gas, they're already more dangerous because they're already in the state which they can ignite. Vapor density is really just how heavy that air is, how heavy that gas is in relation to our normal air. We always say that air has a weight of 1. So anything with a vapor density or weight of higher than 1 will rest in low areas. Anything with a vapor density less than 1 will rise. For instance, methane or natural gas has a vapor density of about 0.5, whereas liquid propane has a vapor density of 1.5. So if we go on a gas leak and we find out that the gas that's leaking is liquid propane, we want to be sure to check in low areas of the home, along window wells, and anywhere else that it can pool where there's not adequate ventilation to push that out. Conversely, if we're going for a carbon monoxide leak, the vapor density of that is 0.96, so it's about 1. So it would be safe to assume that carbon monoxide will be anywhere within a home. The next state of matter or fuel for us is a liquid. Liquid has a mass and volume, but doesn't have a shape except for the shape of the container it's in. If you just pour water on the ground, it's going to just continue to pool outwards until it can, or roll outwards, spread outwards until it can pool in a low area. Specific gravity. Specific gravity is to water what vapor density is to gases. All it is the weight of a substance compared to an equal amount of water. Again, we use the number 1 for the volume for the volume or specific gravity of water. Specific gravity of less than 1 means that whatever it is will float on top of the water. Gasoline has a specific gravity of 0.72. So think about when you go to the parking lot and you see that sheen on top of the water. Well, that means that the gas and oil is floating on top of the water. Something heavier than water will sink. Mercury. Using water to fight a fire involving these liquids, or involving a liquid lighter than water, is going to do nothing but spread it, because you're going to put the water down, whatever's burning will just continue to float on top of the water. Liquid fuels need to be vaporized in order to burn. In order to vaporize, you need to overcome the atmospheric pressure. When something's heated, its pressure increases, those molecules start bouncing around, and then the vaporization rate increases. The vaporization rate is determined by a fuel's vapor pressure and the heat applied to it. Flash point. Flash point is just the lowest temperature at which a liquid gives off sufficient vapors to ignite or flash at the surface. Now, this doesn't mean that it's going to continue to burn, it just means that it will just kind of flash. Now, a liquid that has a lower flash point will be more hazardous than a liquid with a higher flash point. For instance, gasoline's flash point is minus 40 degrees Fahrenheit, whereas vegetable oil is 620 degrees Fahrenheit. Now, that doesn't mean that at negative 40 degrees you're going to have gasoline flashing and ready to go. It just means that it's vaporizing at anything above minus 40 degrees Fahrenheit. It's beginning to vaporize and give off the gases that are needed for combustion. Fire point is the temperature at which a liquid fuel produces enough vapors to support a continuous burning once ignited. And this is usually just a few degrees above the flash point. Boiling point is the temperature at which the evaporation rate exceeds the rate of condensation. Temperature where a liquid turns into a gas at a given pressure. We know that the boiling point, or the boiling temperature for water, is 212 degrees. This is when the water changes from being a liquid into being a gas. Solubility. All that is how well a liquid is going to mix with water. We know some liquids mix better with water than others. For instance, we know that oil and gasoline do not mix with water. Those are hydrocarbon fuels. We know that polar solvents, like alcohol, mix readily with water. They're very miscible in water. Fires that are involving a polar solvent can make water-based extinguishing agents ineffective because they're going to mix, they're miscible with the burning liquid. Next, we have our solid fuels. Our solid fuels have a definite size and shape. Here we have some wood burning. You see you have a hunk of wood. That's how big it is, and that's the shape it's in. Not like a liquid or gas that can change depending on what size container you put it in. If I put that try and put a round peg into a square hole, it's not going to work. That's how solids are. When you heat up that solid, those fuels begin to decompose and create a combustible gas. And those combustible gases, when they're mixed with a sufficient level of oxygen, ignition can occur. This process is called pyrolysis. In this example of wood, as that hunk of wood begins to heat, the first thing that's going to start to happen is the water vapor is going to be driven off. And then as it continues to heat, and once the wood starts to get to about 400 degrees, pyrolysis begins to occur, and those gases are going to start to come off, those combustible vapors. Once those vapors get to about 1,000 to 1,300 degrees, they'll start to ignite, and then we'll have flaming combustion. The size and shape of that wood, or the fuel particles, is going to influence how easily it gets going and how fast it's going to get going. Surface to mass ratio. So if you look at the picture here, we have some sawdust versus some rough cut lumber here. Which of those do you think is going to ignite the most easily? It's going to be the sawdust because it's got a high surface to mass ratio. You might have, let's say, 100 pounds of wood there, but you have a lot of different little surfaces that heat can get to, versus that big hunk of wood that's, let's still say, 100 pounds. You only have so much surface area that can come into contact with that heat. Now, dust from solids and mist from liquids pose possible explosive hazards. That's why we worry about grain bins and grain silos, because not only we already have some fine products with corn or whatever, but then we have the dust, which is just very, very fine. And each of those little particles of dust can ignite at once and create an explosion. The proximity and orientation to the heat source is going to make a big difference. So if you've ever lit a candle, or I'm sorry, a match, and you held it sideways, you know that it burns pretty slowly. But once you take it and you turn it upside down so that the lit end is at the bottom, you realize how fast that will burn. That's why our brush fires, you're going to have fire spread more rapidly uphill than you will downhill or across a flat plane. And then what the fuel is made of is going to influence the combustion and the heat release rate. Anytime you have plastics and synthetics burning, you need to know that there's going to be more heat energy released than when a natural product such as wood burns. Oxygen is the primary oxidizing agent in fires. Besides oxygen, other materials or oxidizers can release oxygen to support combustion. Things such as chlorine. There's about 21% oxygen in the air. Once you start to get less than 21% oxygen, you're going to start to snuff your fire out. But the materials can still ignite and burn in as low as 14% oxygen atmospheres. Once you get below that, that's when you're really going to start to snuff it out, and that's when you start to run into maybe a backdraft potential if you have it in a tight enough area where not enough ventilation or air can get in and fuel that fire. Surface combustion and smoldering can continue at very low oxygen levels. So oxygen itself is not flammable and does not burn. It only supports combustion. Once you add more oxygen, it's going to speed up the combustion and make the fire burn more intensely. And some materials may only burn in an oxygen-rich atmosphere. Materials such as your Nomex hood. Anytime you have a fire in an oxygen-enriched atmosphere, it's going to be a lot tougher. Fuel vapors have to be mixed with oxygen in a proper ratios to burn. If you've ever messed with your 4 gas meters, you've seen that you have an LEL and a UEL. Those are your explosive ranges or your flammable ranges. If you haven't had a chance to mess with those, maybe think about a vehicle. You've heard that maybe it's running a little lean. Well, that means that it's not getting enough oxygen in there to get those fuels to burn. It's too rich. Flammable limit or range is a percentage of vapor in the air that will burn once it's ignited. So in this chart here, we see that we have an upper limit and a lower limit. Everything in the middle of those, in that range, is where we have fire and explosions happening. If you get too low, well, there's just too much normal air in the atmosphere for whatever that fuel is to burn. If you get too high, there's not enough oxygen. It's too much of whatever that fuel is. The flammable ranges can be all over the place depending on temperature and atmospheric pressure and what the product itself is. So earlier I stated the term a self-sustained chemical reaction. So this isn't just a chemical reaction, then it's done. It has to be self-sustaining. It has to continue to keep itself going. So as that fuel burns and oxygen molecules break apart, they form free radicals. Free radicals are electrically charged and reactive parts of molecules. And those free radicals are out there, and then they hook up with the oxygen and they produce new combustion products and increase the speed of the oxidation reaction. Without that, we have like a smoldering fire. That's where we have like our charcoal type examples, as opposed to flaming combustion. So the way some extinguishing agents work is they inhibit that chemical chain reaction. So if maybe you've ever used a chimney bomb or a dry chem extinguisher, you know that all that is just a powder that comes out. That powder doesn't snuff out or remove oxygen from the fire. It doesn't remove fuel from the fire. It doesn't remove any heat from a fire. It inhibits or breaks that chemical chain reaction and keeps it from being able to go on. As I stated before, with the example of rust, a slow oxidation reaction doesn't produce enough heat fast enough to reach an ignition temperature or become self-sustaining, unless we were to confine it into something that won't let that heat dissipate. The size of the compartment or type of compartment that a fire is in is going to determine how fast that fire is going to grow and how hot that fire is going to get. And a compartment, radiant heat is not only absorbed by the compartment itself, but by all the contents. Everything in there is going to absorb that heat. And of course, the hot smoke and gases rise and they heat the upper areas of the compartment. And as the other fuels are heated, more flammable vapors are produced, and they begin to ignite, and then the fire extends, and so on, until you have a fully involved structure. Fuel-controlled versus oxygen or ventilation-controlled fires. When a fire is fuel-controlled, you run out of fuel, you run out of fire. Perfect example of this would be a bonfire you have out in your backyard. As soon as you run out of wood, you run out of wood in the fire, it's all burned up, the fire goes out. There's plenty of oxygen in the atmosphere to support that combustion. Now, an example of a ventilation or oxygen controlled fire would be a candle in a jar. Everything's burning fine, there's plenty of candle left, plenty of fuel. As soon as you put the lid on there, that fire begins to consume the rest of that oxygen, and then the fire goes out. One of the other things that's going to affect the fire development within that compartment is the fuel type. Fuel is going to determine how much heat is released and when it's released. The mass and surface area are going to affect the fire development of that fuel. So, surface to mass ratio, for instance, are sawdust versus our hunk of wood. We know that sawdust is going to start to heat and pyrolyze much faster than that hunk of wood, so it's going to start to spread a fire much faster. We need to be alert to how those different fuels and how they're going to react and how they're going to affect us and the fire growth. Different classes of fires. We have class A, B, C, D, and K. Class A fires, I always remember these, they're ordinary combustibles, so they're apples and about everything else that we have that's just trash. Wood, paper, plastic. Class B, these are flammable liquids and gases. These are the ones that are going to go boom, Class B. Class C is all of our charged or energized electrical equipment. So they're the ones that are charged. Class D, well, it's kind of like me, darn near indestructible metal. No, but the Class D fires, those are aluminum, magnesium, and sodium. You see the picture on the left, the big white flash? that was probably a magnesium fire. These fires actually burn so hot that when you apply water to them, they separate the hydrogen and oxygen molecules, and that supports the combustion process. If you've ever been on a car fire and hit the steering column with water, you've seen that happen. They can be extinguished with water, but you need to use copious amounts of water. Class K fires, those are the ones that you're going to find in your kitchen. You're going to find these with very high heat cooking oils, mostly the ones that are used in commercial processes. The location and availability of additional fuels has a great effect on the fire development within that compartment. In large open buildings, areas can provide exposure to additional fuels. You can also minimize the risk of a high fire load by separating the fuel into compartments. The intensity and speed of a fire will increase when the contents release large amounts of large amounts of heat rapidly. Synthetic furnishings such as polyurethane foam, stuff that's what we use, that are stuffing in our couches, will greatly increase the speed of a fire. This means, for example, in Type 5 construction, the structural components themselves are fuel for fire. Knowing how fire spreads and how it travels through convection and conduction, as well as radiation, we know that contents on upper levels will probably ignite more quickly from the convection of hot gases, and fires originating on upper levels tend to extend downward much more slowly than those starting on lower levels extend upwards. The size of the compartment is really going to have a big effect on how fast that fire grows. If we have a big large compartment, that fire is probably going to develop a little slower than it will in a small compartment, because as the radiant heat spreads, it's going to take a lot longer and it'll take a lot more of it to start to heat the surrounding walls and the surrounding contents. If it's in a big area, you put it in a small area, it's going to heat those things much faster. In regards to ceiling height, if you have big tall ceilings, the amount of smoke and gases that rise, they're all going to accumulate at the top, and it's going to take a lot longer before it starts to bank down and affect the lower level. Ventilation. Can the fire get any air? Can the fire breathe? It's going to affect the growth of fire, and that's going to generate or create what we call our ventilation controlled fires. Ventilation is going to be affected by the size and number and locations of openings. That's why we don't just go and start breaking windows, because anytime we go and break a window, we introduce oxygen to the fire. If we don't have a hose line in place and ready to go, that fire is going to continue to grow, and we might not be able to keep it in check. Compartment fires, room and contents fires, may be fuel controlled or ventilation controlled. Are we going to run out of air or run out of fuel first? Fuel controlled fires. Just like we talked about earlier, are we going to run out of fuel or are we going to run out of oxygen first? Ventilation controlled, are we going to run out of oxygen before we run out of fuel? So ventilation always has to be done in a controlled and coordinated attack. And the reason why that all has to be done that way is because when you open the building up and you introduce air into a building, we can change the direction of travel and increase the growth and the rate in which that fire is spreading. And we might not be able to keep it in check or get it back into check. Every compartment has its own thermal properties. The insulation increases the heat retained inside a compartment and speeds the burning. Some surfaces reflect heat and can increase the speed of burning. And the heat retention properties of the surfaces maintain temperature by absorbing and releasing heat slowly. A lot of these old city houses they're brick and they have plaster and lath walls. Those plaster and lath walls not only hold a lot of heat, but they seem to reflect a lot of heat back into the building or back into the compartment to help ignite all of its contents. What's going on outside can actually have a great effect on what's going on inside with our fires. If you're on your way to a fire and it's humid and cool out, your smoke's going to hang low in the street. Something just to keep in mind when you're looking for a hydrant or watching road conditions, because your vision might be hampered by the smoke. Cold temperatures can also cause the smoke to be white, giving a false impression of what we have going on inside. It might not look like it's that bad. And of course, high winds can really affect our fire behavior. If it can affect our fire behavior when we generate the high winds with a fan, then it can affect the fire behavior when Mother Nature does it. And fire conditions are always changing, sometimes for the better, sometimes for the worse. Our tactical operations can even affect it. It can have a negative effect if we don't execute things properly. They can also have a positive effect when we do things the way we want to do them. We do things the right way. We can affect changes by breaking windows, cutting holes in roofs, or the fire itself can affect those changes by breaking its own windows and burning through the roof. So as the fires develop, they go through a series of stages. Not all the stages are clear and have definite separations, and in fact not every fire even goes through each of the stages. Sometimes those stages are skipped. The first stage of fire development or fire growth is the incipient stage. That's when all three legs of the fire triangle come together and ignition begins. These fires are usually small and confined to the fuel ignited. Remember that all fires occur as a result of some type of ignition. It's during the incipient stage that the radiant heat starts to warm the adjacent fuels. A plume of hot gases and flames rise, just like in this picture, and then it starts to spread across the ceiling, mushrooming or creating a ceiling jet. The heat transfer begins to increase the room's overall temperature. You start to feel it throughout. This is when occupants can easily escape. The transition to the growth stage can happen very quickly at this point. Once we reach the growth stage, the fuel and oxygen are virtually unlimited. There's more than enough to go around. At this point, it's characterized by rapidly increasing heat. The fire begins to influence the compartment's environment as it progresses. This is when we start to notice the most heat transfer and smoke start to bank down. During the growth stage, the fire plume draws in air from surrounding space. The walls and ceilings control the air and increase the depth of the hot gas. And the growth stage will continue while fuel and oxygen are available. It's also during the growth stage that the thermal layering is established. It's referred to as heat stratification and thermal balance. All it is the tendency of gases to form into layers according to temperature. The hotter gases tend to accumulate at upper layers and mushroom out horizontally, and the cooler gases form below them. Radiation from these hot gases heats the surfaces of the compartment and then all of its contents. You can see this smoke here, some of that churning and bubbling, that indicates to me that the air up there, the gases in that level, are doing the same thing. That smoke doesn't just have that shape. That's the shape of all the heated gases. When it's rolling and boiling and bubbling, it's really, really hot up there, and it's starting to near flashover. Higher pressure gases form in hot layers, and they push out and down. That's where we start to get our pressurized smoke from. Low pressure gases in the cooler layers draw in air from the outside of the compartment. In the area where the hot and cooler gases meet is called the neutral plane. The neutral plane exists at the openings where the hot gases and cooler gas, where the hot gases exit and the cool gases enter. Flying water, those upper thermal layers, can cause steam and smoke to circulate at all levels. This is what we call flipping the room or disrupting that thermal balance. When we do that, we're going to decrease visibility, and we're going to bring down all of that superheated gases down onto us. This is where we're going to get the steam burns from. Occasionally we'll start to see some flames moving in the hot gas layer just above us or just above the neutral plane. When these gases start to burn and light off, it means that those gases are all in their flammable range. That's fire gas ignition. That's a major indicator and telltale sign of a developing flashover condition, and it requires immediate action on our part. We need to start cooling that room or that compartment right now. A rollover or a flameover is a condition where those gases at the very uppermost level, the top level, ignite and the flames roll across the ceiling. This is an indicator of a pending flashover, and again, it involves only the upper layer of fire gases, but it's an indicator that the flashover is pending, and again, we need to take immediate action to possibly delay that flashover and get out of the area. Once we start to recognize those signs of imminent flashover, we need to take immediate action. We need to start cooling that room, and we need to start cooling that room right away. If we're only thinking about exiting that room or compartment, we're already behind the 8 ball. A flashover is described as a non-survivable event. In fact, a lot of guys that say they've been in a flashover were never really in one. They were only in a rollover, which is still a very significant event. However, it still wasn't a flashover. A flashover is the rapid transition between the growth and fully developed fire stages. It's not a specific event such as ignition. It's the stage of a fire where the area becomes heated to the point where all the flames flash over the entire area at once. This room or this building here has just flashed over and is now in the fully developed stage. During these pre-flashover conditions, we have thermal radiation feedback. What's going on is that fire is burning, the hot gases at the ceiling level are starting to cause radiant heating of all the combustible materials. Everything in that room starts to pyrolyze, and once all of those gases start to reach their ignition temperature, everything ignites at once. Everything becomes fully involved in fire in those seconds. Again, flashovers happen in seconds and cause complete fire involvement of a compartment. This is a flashover situation right here. They occur in enclosed spaces like a room or enclosure, and everything in the room that can burn does burn. So just before that flashover begins, we talked about some of the signs you might see, but this is one of the signs that you'll definitely feel. The temperature will start to rapidly increase. You might start to notice some other fuels becoming involved. Things that are not right next to the fire are starting to light off and ignite. That's a major sign that something's about ready to go wrong. Everything in the room is starting to give off their combustible gases and it's ready to go. In order for this flashover to occur, the fuels have to have enough heat energy to develop the conditions, and there has to be enough oxygen to reach the flashover. So these fires aren't yet controlled by fuel or ventilation. So we talked about those temperatures starting to rise and rise rapidly. How hot are we talking? Well, over 1,500 degrees. Anything in that room will not survive, including firefighters and our turnout gear. Our SCBA and structural protective gear will be destroyed. Your face piece is only rated to about 500 degrees, and by that point it will have exceeded it by at least 3 times. It will have melted and you will be dead. Flashovers, they're going to develop with little warning. They happen quick, so you have to be alert to the signs and see what's going on before they happen, before it's too late. Flashover from an open flame can be as short as 90 seconds in a residential fire test, or it may never occur. No one can accurately predict when a flashover is going to happen. This here is a picture of a flashover simulator. If you ever get a chance to go on one, I highly recommend it. It's almost like witnessing a rollover. What you'll do is you actually sit in a compartment just below another compartment that does flash, and so you'll see that flash, and then the flames will kind of roll over you. It's pretty hot and pretty intense. It'll really give you a good appreciation of how hot it's going to get. Unfortunately, we've started to expose ourselves to flashovers more often due to our better equipment, better notification of fires, insulation in structures, and more combustible furnishings. So we're getting there faster, and when we get there, we have better equipment so that we're more insulated from the fire. We go deeper and farther and faster. And then we have more combustible furnishings within all the buildings. Again, some more signs of potential flashover with the heat buildup, the rollover, thick dark smoke, free burning of fire, and then a significant bidirectional airflow. Air in and smoke out. Once you see that smoke starts to really push out pressurized, it's a big indicator that, hey, some things are about to go down and it's not going to be good. Some flashover survival techniques. Pay attention to the situation and recognize the signs and recognize them early. That's going to give us the best chance to get out or to avoid that flashover. Keep ourselves orientated and know where our exit is. Keep calm and think. Hopefully at this point we already have all of our full protective equipment on, and let's go ahead and keep it on. We need to know our point of no return. A firefighter can travel about 2.5 feet a second without a hose, and we have about 2 seconds to exit an area when a flashover occurs. So doing that math, that means escape is possible if I'm within 5 feet of an exit and I recognize the signs immediately. If I'm 6 feet into a structure or into a room, I'm not going to make it out on time. If a flashover does occur, you need to get as low as possible, open the nozzle on a full fog overhead, and evacuate the area immediately. These are the conditions that have firefighters diving out of third-story windows without any regard or worry in the world about what's below them. They know that outside and falling 3 stories is much better than being inside in those conditions. There's one other step that I might add to that, and that would be to, if you can't do any of these 3 things, it'd be to put your head between your legs and kiss your butt goodbye. Fully developed stage, this is just after a flashover occurs, and everything that can burn is burning. All the heat that's going to come out of that building is coming out now. These fires can become ventilation controlled, and large amounts of unburned gases may be produced. These unburned gases can move into adjacent spaces and ignite in there and continue the spread of fire. Decay stage. After everything started to burn up, the rate of release begins to decline. Fire becomes fuel controlled, and flames and temperature begin to decrease. There's some glowing embers that can result in moderately high temperatures for some time. This is also the period when we start to worry about a backdraft. So, as the fire is burning, large amounts of hot unburned gases can collect in all the unvented areas without enough oxygen to ignite. Remember that we have our fire triangle. We have heat, oxygen, and fuel. In this situation, we have all the heat and all the fuel but no oxygen, so we're just waiting for that third leg. The more the fuel and air mixture is confined, the more violent a backdraft will be. So if we have a small container or a really tight container, we introduce some oxygen with through a small opening relative to the container or compartment, the more violent the backdraft will be. Backdraft indicators. We'll have smoke under pressure. That black smoke will start to change to a dense yellow-gray color. We'll have fire confinement with excessive heat and little or no visible flame. The smoke will start to leave in puffs. It'll be almost like the building's breathing. You'll see smoke-stained windows, muffled sounds, and you'll see the smoke start to pull back in. You might have a sudden inrush of air when an opening is made. If fire's consumed all the air or all the oxygen in there, and it's searching for more. It's pulling it in. The effects or the severity of the backdraft are going to vary depending on the volume of flammable products of combustion, how confined or tight that building is, where the ignition occurs, and how much air and fuel and how fast you mix those together. The smoke explosion is a fire gas ignition. It's when the accumulated flammable products of combustion reach their flammable range. As the smoke travels from the fire area, it can cool and accumulate and contact an ignition source. It may occur in a void space near the fire or uninvolved areas. So if we want to control that fire, we want to stop the fire, we have to remove one of those legs of the fire tetrahedron, one of the elements of it. The most common way for us is to reduce the temperature. We usually do that by using water. We just have to have enough water to overcome the BTUs being thrown out by that fire. We can use water to cool down the burning gases and reduce the temperature of those combustion byproducts, but we need to recognize that cooling with water will not reduce the vapor production in low flash point flammable liquids enough to stop burning. Remember that, for instance, gasoline had a flash point of minus 40 degrees Fahrenheit, so there's no way we're going to be able to put water on it so that we can cool it to below minus 40 degrees Fahrenheit. Cooling with water also reduces the potential for flashover. Water is going to be most effective when we're able to get it to convert to steam. Remember, at 212 degrees, water starts to boil and it converts from being a liquid to a gas. It converts to steam. When it does that, it expands 1,700 times and is converted to steam. We do have to be careful when we start to get a room real steamy. That's when we're going to reduce visibility, cause some steam burns, and disrupt that thermal balance. We talked about that earlier. We can control some of that steam production though. We need to use a good nozzle technique by turning the nozzle, the bumper all the way to the right and moving to a smooth bore nozzle versus a fog pattern. A straight bore versus a fog pattern. Applying the correct amount of water. Applying the water in the most effective method for the conditions. Sometimes we do need to use a fog pattern. There's other times we need to just use a straight stream or a solid stream. One of the other ways to attack one of the legs of the fire tetrahedron is to remove the fuel. The simplest method to do that is just to allow the fire to burn until all the fuel is consumed. Sometimes we do this to prevent further environmental damage through the runoff. So if we have something burning, maybe some type of pesticides or other hazardous material, we know that if we go and we throw 1,000 gallons of water on there, we're going to have 1,000 gallons of runoff going into our creeks and streams, so it might be better to just let it burn itself out. Very simple way to remove fuel from a lot of fires is just to shut off the valve. We can cut off the flow of flammable gas or liquids. We're great. Or we can move solid fuels out of the path of fire. That's the same thing we do when we go on a brush fire, when we rake our fire lines. The other way is oxygen exclusion. We can just pump an area full of a gas, an inert gas such as carbon dioxide, to displace the oxygen to stop combustion. Something to keep in mind when you're using oxygen exclusion methods such as carbon dioxide or a CO2 extinguisher. Those are a simple asphyxiant, so you can't use that in a confined space without a respirator for yourself. We can blanket a burning flammable liquid with a foam that's used to exclude oxygen and stop the burning. You can see that's what these guys here are doing. One thing to maybe take note of is that they are standing in that foam blanket, and everywhere that they create a hole, oxygen can be reintroduced and the fire can flare up right there at them. We can inhibit the chemical chain reaction. I mentioned this earlier when I talked about using a dry chemical extinguisher. Those don't necessarily smother the fire or prevent it from having oxygen. It just breaks that chemical chain reaction. Halogen and halogenated agents are examples of a chemical chain reaction or a chemical flame inhibition. A lot of times these are really good and effective for gas and liquid fuels, but they may not extinguish non-flaming fires like a smoldering fire because there's no chemical chain reaction that creates that flaming combustion to inhibit. We've got to do everything we can to control the flow of smoke and heat. That's going to help provide safety for us and any of the building occupants. That's why we do ventilation. We want to try and direct that smoke and heat where we want it. However, it's got to be a coordinated attack. We can't do it whenever we want and however we want. Improper ventilation can influence fire behavior, can result in the introduction of wind from the outside into the structure. This is a big deal, especially with high rises. We can have wind-driven fires. It can drive smoke and fire into uninvolved areas and onto firefighters. Tactical ventilation is the planned, systematic, and coordinated removal of smoke, gases, and heat from a building and the replacement of them with fresher air. Must be coordinated with suppression activities for proper fire control. If you go and bust open a window and allow a fire to grow in an area without a hose line in place, you're going to let that fire get too big to put back in check. Even coordinated tactical ventilation will increase burning in ventilation controlled fires. That's why you have to have that hose line there and ready to go. You got to have an understanding of fire behavior for safety and proper extinguishment techniques. If you don't know how the fire is going to behave, you're not going to know how to attack that fire. A lot of guys have been hurt or killed because they didn't know what was going on and they didn't pay attention to those changing signs. Only after we know how to look at that fire and determine what's burning and where it's burning can we kind of determine where it's going to burn to and how it's going to get there. Will we know how to react and how to prepare ourselves for what's about to happen? Also, we can prepare for how to mitigate that incident and extinguish that fire. I appreciate your guys' time in watching this video. Hopefully it wasn't too bad. Fire behavior can be somewhat of a dry subject. I highly recommend reading the book. If you haven't been reading your book, that was one of the biggest things that helped get me through the academy, was staying on top of it. By the time you get to class, if you're just waiting for the PowerPoint presentation or waiting for the instructor to tell you everything, you're kind of behind the 8 ball. So hopefully you've got something out of this and maybe you've generated a question or two and we can talk about them on Tuesday. Thanks, and we'll see you then. Be safe.